Court is now in session. Today we are here to determine the truth of the statement. All even numbers are divisible by 4.
Your Honor, using the method of direct proof, I will show that since even numbers are multiples of 2, they must also sometimes be divisible by 4.
Objection!
That's misleading. Not all evens are divisible by 4. For example, 2. 2 is even, but not divisible by 4. That's a counterexample. Very logical. Statement. Do you have anything to say for yourself?
I thought being even was enough.
Order! It is clear. The statement is disproven by counterexample. Case closed.
Hi guys, we are Group 7.
And for today's video, our topic will be all about methods of proof and disproof.
Hi guys, I'm Ronald and I'm one of your teachers today.
Hey there, my name is Ayana. A fun fact about me? Well, I used to be the former female national record holder for both 3x3 and 3x3 OH in terms of speed cubing. Well, that's all. Let's get right into the topic. Before we proceed to the lesson, let's have a look at the learning objectives. Today, our topic will be all about proof and disproof. Given the conditional P to Q, the process of establishing that the conditional is true by using the laws of logic and the other known facts constitutes a proof of the conditional, while the process of establishing that the conditional is false is called disproof of the conditional. Under types of proof, we have 3 and 2 under the types of disproof. For types of proof, we have direct proof, indirect proof, and proof by contradiction. Under types of disproof, we have disproof by contradiction and disproof by counterexamples.
Direct proof. Proving if P then Q true. Step 1. Hypothesis. Assume that P is true. Step 2. Analysis. Starting with the hypothesis, apply laws of logic and other facts and infer that Q is true. Step 3. Conclusion. If P then Q is true. Example number 1. The sum of any two even integers is an even integer. Let x and y be any two even integers. X equals 2a and y equals 2b. X plus y equals 2a plus 2b equals 2 times the sum of a plus b. 2a plus 2b plus 1 equals to 2 open parenthesis 2ab plus a plus b close parenthesis plus 1. Example number 2. The sum of any two odd integers is an even integer. Let x and y be any two odd integers. X equals 2a plus 1 and y equals 2b plus 1. X plus y equals the sum of 2a plus 1 added to the sum of 2b plus 1 equals 2a plus 2b plus 2 equals 2 times the sum of a plus b plus 1. Example number 3. The product of any two odd numbers is an odd number. X equals 2a plus 1 and y equals 2b plus 1. xy equals the sum of 2a plus 1 is multiplied to the sum of 2b plus 1 equals 4ab plus 2a plus 2b plus 1 equals 2 open parenthesis 2ab plus a plus b close parenthesis plus 1. Example number 4. The square of any odd integer is an odd integer. Let n be an odd integer, so n equals 2k plus 1. N squared equals the sum of 2k plus 1 is multiplied to 2 equals 4k squared plus 4k plus 1 equals 2 open parenthesis 2k squared plus 2k close parenthesis plus 1. Example number 5. If a number is a multiple of 6, it is also a multiple of 3. Let n be a multiple of 6. Then n equals 6k. N equals 3 times 2k.
Moving on to indirect proof. Proving P to Q is true. We have 4 steps here, where step 1,
we will be finding the known fact. Step 2, hypothesis. Assume that Q is true. Step 3 is analysis. Starting with the hypothesis, apply laws of logic and other facts and infer that P is false and therefore P is true. Step 4, conclusion. If Q and P are true, then Q to P is true and therefore P to Q is true. There are examples. Example number 1. If x2 is even, then x is even. The contrapositive is, if x is not even, which means it's odd, then x2 is not even. Therefore, the original statement is true. Next example. If 3x plus 2 is odd, then x is odd. The contrapositive is, if x is not odd, then 3x plus 2 is not odd. In this case, x will be 2k. So x will be replaced by 2k. As you can see there, 3 will be multiplied by 2k plus 2. Therefore, the original statement is true. Example number 3. If x is an integer and x2 is odd, then x is odd. The contrapositive is, if x is even, then x squared is even. X will be replaced again by 2k, and the answer is 4k squared. Therefore, the statement is true. Example number 4. If a plus b is even, then a and b are either both even or both odd. The contrapositive is, if a and b are not both even or both odd, then a plus b is odd. A will be valued 2k and b will be valued 2m plus 1. Therefore, the original statement is true. For the last example, if a number is a multiple of 4, then it is a multiple of 2. The contrapositive is, if a number is not a multiple of 2, then it is not a multiple of 4. An odd number is never a multiple of an even number, so this is true. Therefore, the original statement is true.
Proof by contradiction. Proving if P then Q true. Hypothesis. Assume that if P then Q is false. Therefore, hypothesis is P is true and Q is false. Step 2. Analysis. Starting with hypothesis, Q is false. Apply laws of logic and other facts and infer that P is false. This contradicts the assumption that P is true. Step 3. Conclusion. We infer that if P then Q is true because of the contradiction arrived in the analysis step. Example number 1. The square root of 2 is an irrational number. Assume the opposite. The square root of 2 is rational, so it can be written as BA in simplest form. Thus, the original statement is true. Example number 2. There is no largest prime number. Assume there is a largest prime number, P. Consider a new number, Q, equals open parenthesis 2, 3, 5, and so on and so forth until P. Close parenthesis plus 1. Q is either prime or divisible by one of our primes, but it has a remainder of 1 for all of them. This is a contradiction. Therefore, our assumption was false. Example number 3. There are no integers a and b such that 24a plus 18b equals 1. Assume the opposite. There are integers a, b such that 24a plus 18b equals 1. Factor out 6. 6 open parenthesis 4a plus 3b close parenthesis equals 1. This means 1 is a multiple of 6. This is a contradiction, so the original statement is true. Example number 4. If a2 is odd, then a is odd. Assume the opposite. A is even, then a equals 2k. So a squared equals the square of 2k equals 4k squared equals 2 times 2k squared. This means a2 is even. This contradicts our premise that a squared is odd. Our assumption must be wrong, so a is odd. Example number 5. There is no smallest positive rational number. Assume there is a smallest positive rational number, r. Consider the number 2r. This is also a positive rational number and it is smaller than r. This contradicts our assumption that r was the smallest.
Disproof by contradiction. The first type of disproof. We have 3 steps here. Step 1 is hypothesis.
Assume that P is true, Q is true, and hence P to Q is true. Step 2. Analysis. Starting with the hypothesis, apply laws of logic and other facts and infer that assumption is wrong and hence P to Q is false. Conclusion: P to Q is false. Example number 1 for disproof by contradiction. The sum of two odd numbers is odd. Let's assume that this statement is true. We've already proved using a direct proof that the sum of two odd numbers is always even. This new assumption that their sum is odd contradicts our known fact. Therefore, our assumption is false and the original statement is disproven. Example number 2. All numbers divisible by 4 are not divisible by 2. Let's assume that this is true once again. A number divisible by 4 can be written as 4k, which is the same as 2 multiplied by 2k. This means any number divisible by 4 is also a multiple of 2. This contradicts our assumption that such numbers are not divisible by 2. Thus, the original statement is false. Next example. If a number is an integer, it is always a whole number. Let's assume that once again this is true. Consider the number -5. It is an integer, but it is not a whole number. This is a contradiction. Therefore, the statement is false. Example number 4. All rational numbers have a terminating decimal representation. Let's assume that this is true. Consider the rational number 31. Its decimal representation is 0.333 and so on, which is a repeating decimal, not a terminating one. This is a contradiction. Therefore, the statement is false. Example number 5. Every polynomial has at least one real root. Let's assume that this is true. Consider the polynomial f to x is equals to x squared plus 1. If we set it equal to 0, we get x squared equals to -1. The roots are x is equals to square root of -1, which is equals to positive minus I, or imaginary, which are not real numbers. This contradicts our assumption.
Disproof by counterexample, proving if P then Q false. We know that the quantified statement for all x, P of x is true, is false if there exists at least one element as such that P of A is false. Hence, we consider a single case such that P of x is false, and this single instance proves that the original proposition is false. Example number 1. All prime numbers are odd. The number 2 is prime, but it is an even number. Therefore, the statement is false. Example number 2. If a number is a multiple of 2, then it is a multiple of 4. The number 6 is a multiple of 2, but it is not a multiple of 4. Therefore, the statement is false. Example number 3. All numbers that end in 5 are divisible by 5. Our counterexample is 0. 0 is divisible by 5, but does not end with a digit 5. Example number 4. For any real number, x squared is greater than x. Our counterexample is x equals 21. 21 times 2 equals 41, and 41 is not greater than 21. Example number 5. The sum of any two irrational numbers is irrational. Our counterexample is the square root of 2 and square root of -2. Both are irrational, but their sum is square root of 2 plus square root of -2 equals 0, which is a rational number.
Let's have a recap. Definitions. Proof. The process of establishing that a conditional statement P to Q is true by using the laws of logic and other known facts. Disproof. The process of establishing that a conditional statement is false. There are three types of proof: direct proof, indirect proof by contrapositive, and proof by contradiction. Under direct proof, we have a straightforward method where you assume that the hypothesis is true and then, through a series of logical steps, infer that the conclusion Q is also true. Under indirect proof by contrapositive, basically, you assume the negation of the conclusion is true and show that it leads to the negation of the hypothesis, thus proving the original statement. Proof by contradiction, you follow a chain of logic that leads to a contradiction which proves that your initial assumption was wrong and the original statement must be true. While for the two types of disproof, we have disproof by contradiction and disproof by counterexample. Under contradiction, You assume that the statement P to Q is true and then show that this assumption leads to a logical contradiction. Because the initial assumption leads to an absurdity, it must be false, thus disproving the original statement. While under counterexample, this is the simplest way to disprove a universal statement. You only need to provide one single case where the statement is false. That is it for today's video. We hope that you learned something. Thank you so much.